All right, the next and really the last piece of this puzzle I've been developing here for our last few videos is the notion of a regular partition as opposed to a general partition. Everything we've done so far has been a general partition. A regular partition has the following requirement. All subintervals are the same width. Or another way to say this, the norm, well, let's say it this way. All delta x sub i's are equal. So if this is A and B, when we make just a generic or a general partition, there's nothing that requires they be the same width. But if we have a regular partition, then the requirement is, however many you have and however bad my picture is, the subintervals must all be the same size. Is it clear then delta x number 1 and delta x number 2 are equal, which is equal to delta x number 3, and that's equal to delta x sub n. And since they are all equal, there's no need to subscript them. We simply talk about delta x. So if you have a regular partition, then all the delta x sub i's are the same number, which we denote delta x. And so if we have our Riemann sum, I goes from 1 to n f of c sub I. We do not need to write delta x sub I because they're all the same size. So if we have a regular partition, you don't need to subscript this. All right? Now, the next piece is this. If you refine, whenever you refine a regular partition, what were the requirements? You need to keep the intervals you have. You must include at least one more. The norm must get smaller. So if I just chop this one, the norm hasn't changed because the maximum is still here. What you're not allowed to do is this. You're not allowed to chop this one here and then this one over here. If we have a regular partition, then it is assumed, until further notice, for everything we will do, this is the case. For a regular partition, anytime you refine a regular partition, then whatever you end up with must also be a regular partition. That means this. If you cut this one into 3 equal pieces, they must all be cut into 3 equal pieces. If you cut this one into halves, then they must all be cut into halves. If you cut this into fifths, they must all be cut into fifths. If you start with a regular partition, then a proper refinement is you must end with a regular partition, so that delta x is the same for that partition and any refinement of it. Those delta x's are the same. So, with that proviso, then we can say this. Suppose I have A, B, and suppose I have 3 equal pieces. So in this case, n is 3. Regular partition. We will say this. For everything we do, from here on out, everything we do, unless you're specifically told otherwise, everything we do from here on out, everything we do will be with a regular partition. It turns out that it can be shown that any computation you can do with a regular partition can be done with a general one and vice versa. It's just for our purposes, the regular partition, the algebra, among other things, is much easier. So, from here on out, we will assume regular partitions. All right? Now notice, in this case, I have n equals 3. Now, if I cut this into equal pieces, now I have 0, 1, 2, 3, 4, 5, 6. Now I have n equals 6. Notice, delta, the norm of the delta, the norm has gotten smaller but n has gotten larger. Now, how do I make delta even, the norm of delta smaller? How do I make this norm even smaller? Suppose I cut this into 4 equal pieces. Then they must all be cut into 4 equal pieces. And now I have 24. Notice, as the norm of delta gets smaller, as the norm of the partition gets smaller, n gets larger. And because this is a regular partition, anytime you make n larger, if I cut these in half, well, they must all then be cut in half, and that means the norm has gotten smaller. So, the norm of the partition gets smaller, again, assuming we're a regular partition, and I'm going to stop saying that. From here on out, anytime I say the word partition, we assume that means regular. So, as the norm of the partition gets smaller, that is logically equivalent. That's true if and only if n is getting larger. And so, when we talk about the limit of this Riemann sum, let me rewrite this. Now we may simply write delta x. Now, before we had limit as norm goes to 0, the computation is much more straightforward. It doesn't seem easier, but the computation is much easier. Instead of saying norm of partition go to 0, norm of the partition goes to 0 if and only if n goes to infinity. So we take the limit as n goes to infinity of the Riemann sum. So this limit of the Riemann sum, that is the definition. That's the definition of the definite integral from a to b, f of x dx. How to compute this we'll discuss later. Some terminology. The a and the b, they are called limits of integration. The limits of integration. They probably should have been called the endpoints of integration, but that ship has sailed. The fact that these are called limits of integration doesn't really mean the same thing as this limit. The terminology gets a little muddled here, but you'll get used to it. Everyone does. These are called the limits of integration. So if I have a to b, limits of integration. The upper one has a special name. The upper limit of integration is called the upper limit of integration. The lower limit has a special name. The lower limit is called the lower limit. The upper limit and lower limit, those are the limits of integration. And so the limit of a Riemann sum is the definite integral. Again, how to do this computation we'll deal with later on, but that's the terminology, those are the symbols we use, and all this comes from the limit of a Riemann sum using a regular partition.